In this video, I will be demonstrating a method of measuring X-ray beam area using a Raspberry Pi Zero and computer vision. I will be walking you through how to go from a recording of an exposure cycle of a panoramic dental X-ray to a masked video with measurements of area and dimensions displayed. Here is the camera module and where it plugs into the Raspberry Pi, the USB data port, the USB power port. The Raspberry Pi is powered by a mobile phone power bank, which when turned on will then start up the Raspberry Pi. The Raspberry Pi can be attached to a holder such as the OctoPi by Pi Moroni using plastic screws which come with the OctoPi. Here I will now demonstrate how to power up the Raspberry Pi. Simply power on the power bank and the green light will show on the Raspberry Pi indicating that it has powered up correctly. Here you can see the setup on the panoramic X-ray unit, also known as an orthopantogram or OPG. On the left is the Raspberry Pi camera mounted to the OPG using a mobile phone holder for a car. On the right is the X-ray detector unit. Attached to the detector unit is a phosphor sheet. As can be seen, a chest pattern was printed and taped to the front of the phosphor sheet. This chest pattern is used both as a reference object for pixel size calibration and as a tool for perspective transformation. Perspective transformation was performed by taking an image of the chest pattern. The homography of the chest pattern was calculated and a target homography was defined such that the target homography would correspond to an image of the chest pattern that is parallel with the image plane of the camera. This is shown schematically using the top two images. In the top left image, the red and green lines correspond respectively to the width and height of one of the squares. These two lines have slightly different lengths due to angulation of the camera. On the right, after perspective transformation to the target homography, the height and width of the square are equal, as indicated by the two red lines. To calibrate pixel dimensions, the actual square width in millimeters was divided by the number of pixels corresponding to the red line. To verify the accuracy of using the perspective corrected image as a reference object, the perceived distance from the chest pattern to the image plane was calculated. The same chest pattern was placed at the perceived distance from the camera and approximately parallel to the image plane. An image was then taken of the chest pattern and the pixels calibrated as previously described. The pixel dimensions using both methods were found to be equal. Here is a demonstration of how to run the computer vision code. The code is run from the terminal as shown. Once video data is loaded, the user is asked to enter the width of a chest square in millimeters, after which perspective transformation and pixel calibration is performed. Then the user is asked to select a region of interest using the cursor. After some processing, the region of interest is segmented from the rest of the image. By segmenting a range of frames using the same region of interest, average size measurements and their standard deviations can be calculated and displayed on a masked video. Here you can see the full-length masked video. As can be seen on the right, by using dark light conditions, improved accuracy can be achieved. It should also be possible to achieve additional enhancements by using more advanced camera technology. Thank you for listening, and please visit my GitHub for more information.